Okay, number 5 is asking us to graph the function, and specifically, this is a piecewise function. We are going to use different function definitions according to what x values we're plugging into the function. So you can see highlighted in yellow, 3x plus 3. We use that for any x values less than or equal to -1. So that's this section on our graph of the x-axis. That middle function definition, 3x squared minus 2, we're going to use that for x values between -1 and +1, including +1. And then you can see for our final function definition, 1 minus x squared, we're going to use that for x values greater than 1. When we have a piecewise function with 3 parts like this, what I like to do is set up 3 separate little t-tables. So for the first part, this is for 3x plus 3, which is for x values less than or equal to -1. Fix that up. And here we go, x less than or equal to -1. So that means x values like -1, -2, -3. 3x plus 3 is a linear equation, so I don't need a whole bunch of points because I know that's going to be a straight line. When I plug in -1, I get -3 plus 3, which is 0. When I plug in -2, I get -6 plus 3, which is -3. And when I plug in -3 for x, I get -9 plus 3, which is -6. Let's plot those points. -1, 0. That's right there on that x-axis. And that's going to be a solid point because this part of the function is for x less than or equal to -1, including -1. -2, -3 is about here. -3, -6, about there. So we're going to have a nice straight line that continues to the left, but has an endpoint on the right because that is only the function for a piece of our graph, just for x values less than or equal to -1. Next up, we have that middle function definition. This is our 3x squared minus 2. And this is for x values between -1 and 1. But we got to be careful there. -1 is not actually included in this part of the graph, but I include it in my t-table because I need to be able to draw my graph going all the way right up to -1 without including it. So I need to include values by like -0.8 and -0.9 and getting closer and closer to -1. So I do that by finding that point and including it as an open circle, meaning I don't include that end point. So if we plug in -1 into 3x squared minus 1, -1 squared is 3. So we just get 3 minus 2, which is +1. We put a 0 in there, we get 0 minus 2. And if we put a 1 in, we also get +1. So we'll plot those points. Again, -1 is an open circle. I didn't quite hit that in the right place, did I? Let's see if we can make this a little bigger. -1, 1 is an open circle. 0, -2, and 1, 1 is a closed circle because we include that endpoint, +1, but not the -1 endpoint. And then we draw, it's going to be a nice little parabola connecting those 3 points, just as good as you can draw it. That's not perfect, but it's good enough. There's the middle part of our graph for values between -1 and +1. And then finally, our last part of the graph for x values greater than 1. Again, even though it's strictly greater than, I'm going to include 1 because I got to go all the way right up to it without actually including the endpoint. So when I put a 1 in for x in the blue function, 1 minus 1 is 0. 2 squared, so we get 1 minus 4, which is -3. And 3 squared is 9, so 1 minus 9 is -8. Plot those points. Again, that 1, 0 is going to be an open circle. 2, -3, and 3, -8. Those points might look almost like a straight line, but they're not. That blue function is an x squared, so that is going to be a parabola because it's a quadratic function. So again, just sketch it the best you can. It's going to keep going to the right, but not to the left because that blue function is only for x values greater than 1. Next up, we're going to start talking about transformations. We're given a function here, and then we have a couple questions. The first question is, what is the parent graph, f of x? So if this thing didn't have any transformations on it, what would the function look like? Well, we wouldn't have that 1/3 in the front. We wouldn't have the -2 or the -4. So this parent function would just be x cubed, okay? That's our parent function. Then we want to describe the transformations that are going on here. And we got 3 different things going on. We got that 1/3 in the front. Actually, let's start in the parentheses, x minus 2. Anything inside your parent function, in this case, inside that cubed exponent, that's going to be a horizontal change. So that x minus 2 is going to be a horizontal. Specifically, when we add or subtract a constant, it is a shift. And this shift happens to go to the right by 2 units. So that's that -2 in the middle. Then we have our 1/3 out front. Anything that is outside of that cubed exponent, that's going to be a vertical change. When we multiply or divide by a number, that's going to be a stretch or compress. Specifically here, since we're multiplying by a number less than 1, which is kind of like dividing by a number, that is a compression. So this is a vertical compress by a factor of 3. We take the reciprocal of that fraction because we are dividing by 3, compressing by 3. If you say compressing by 1/3, it's kind of like a double negative. We are already telling the direction of the change. Compress implies division or shrinking by 3. And then that -4 at the end, again, that is outside of our original parent function, so it is a vertical change. Since we are adding or subtracting a constant, it is also a shift. And the -4 goes down by 2 units. And then we need to sketch this graph. So I think maybe I'm going to start by looking at what that parent function looks like. Okay, that f of x equals x cubed. I happen to have some of these values memorized. -2 cubed is -8. -1 cubed is 1. -1. 0 cubed is 0. I ran out of little room here. 1 cubed is 1. And 2 cubed is 8. So we can kind of sketch that in just for our reference. -2, 2, 4, 6, 8. Nope, that's a 1, 2, 7. Here's 8. And +2, 2, 4, 6, 8. So this is what our x cubed function looks like. It has this kind of little wiggle in the middle, a little inflection point there. It keeps on going down. So that's what our parent function looks like. What we're going to do is we're going to take that function, we're going to shift it and compress it, and we're going to see what it looks like. So let's build ourselves a new t-table. So when I take sort of that 0.00, that's kind of my reference point for this parent function. When I take that, first of all, a stretch or compress doesn't change the number 0 because when you multiply or divide 0 by anything, you get that same number back again. So that 0.00 is just going to be affected by our shifts. So it's shifted 2 to the right. Well, that was a 4 right there. 4 down. Sorry, did you catch that? 4 down because it was a -4. Shifted 2 to the right and 4 down. So this is going to be the new inflection point or wiggle point on our graph. Let's double check that. If we plug in -2 for x, we get 2 minus 2, which is 0. 0 cubed is 0. 0 minus 4 is -4. Yes, that worked out. There is our compression point. So from there, since we know that's kind of the middle setting our curve now, we probably want to try x values on either side of it. We might want to try x equals 3 and x equals 4. And this is where maybe I want to show you how that table button works on your calculator. So if you press the table button, if there's anything in there, press clear. We can input this function into our calculator. So 1/3. Parentheses, x, this is the x variable right here, as an x on it, it's next to the 4, x minus 2 quantity cubed, and I'm going to arrow out of that exponent and then have a -4 at the end. Once you have your function typed in, hit enter, and then you can fill in these numbers. I usually just worry about the auto or the ask, and here I want it to be ask. I want it to ask me what x values to use, so I hit OK. There's going to be some in here already, but I already decided I'm interested in x equals 3. So I'm going to type a 3 right there and hit enter. It will just type over what we already have. Negative 11 thirds. Okay, that's a little maybe tricky to graph. So here's what we can do. If you arrow over to that number negative 11 thirds and you hit this double arrow button, it will tell you that is negative 3.67 or roughly negative 3.7. So the point positive 3, negative 3.7, that'd be maybe about right there. 4, I'm going to stick in there too. When I put in, go back to my x's, when I put in 4, enter, that gives me negative 4 thirds, which is approximately equal to negative 1.3. Nope. Yep, I plotted that first point wrong. Sorry, let me back up. This point was, did you catch that? X equals, oh no, I was right. X equals 3, negative 3.7. And then x equals 4, negative 1.3, maybe about there, okay? Let's try also, how about 1 and 0? When I put a 1 in for x, and you can do this by hand also. You could calculate what this is, 1 minus 2 cubed times 1/3 minus 4. You can calculate that by hand. When I put in x equals 1, I get negative 13 over 3, which is negative 4.3. I just think the decimals are way easier to graph than the fractions. So 1, negative 1, 2, 3, 4.3, about there. And 0 is going to be negative 4. I can do that one in my head. 0, 1, 2. Nope. Oh, it's not. Silly. Let's type it in here. Let's not do it in my head. 0 is going to be, not even close. 0 is negative 20 thirds, which is negative 6.7. 1, 2, 3, 4, 5, 6.7, about there. And maybe because you know the shape, you can start to see, remember, it has that wiggle in there. So it's going to kind of shoot out here and keep going down and then wiggle up there. You can see, I don't know if you can tell, that this is a little broader and a little flatter than our original function. And that's because of that horizontal compression, kind of squished it all down, like putting it in a trash compactor. Okay, next up, write an equation for the function whose graph is described. We want the shape of f of x equals the absolute value of x. So there's our parent function, but we're going to take that and shift it 6 units to the left, 8 units up, and reflect it in the x-axis. Okay, so we want to write the equation of a function. So let's start out. Let's call our function g of x, since our original one was f of x. We got a couple things going on here. We want to shift it 6 units to the left. That's a horizontal change, so that needs to go inside my absolute value symbols. Horizontals are inside. 6 units to the left is a plus 6. Plus 6 moves it to the left. 8 units up, that's a vertical change, so that's a plus 8 outside of the absolute value symbols. And then reflected in the x-axis, reflected over the x-axis, that's really a vertical change. So that's a negative sign that goes on the outside of my absolute value symbols. Another transformation problem, we want to use the graph of f of x equals the square root of x to write, we want to use, that should probably say use the equation f of x equals square root of x to write an equation for this function represented by the graph. So they're telling us this is a square root function. Do you guys remember what the square root function looks like before you transform it? It has the point 0, 0 and 1, 1. And then for 2, it looks something like this before we transform it. So this graph is oriented the opposite direction. It has been reflected. It has been actually reflected twice, right? Because instead of going uphill and kind of convex up here, it's going sort of to the left and downhill down here. So this has been reflected over the x-axis so that it would come down here instead. And then it's also been reflected over the y-axis so that it goes in this direction. So we got a double reflection going on to get it oriented in the way that it is here. So that would be a minus, negative, minus on the outside, minus on the inside for the vertical and the horizontal reflection, or reflecting over X and reflecting over Y. So if we reflect it twice, this is now the graph that we have. Let me actually draw it in there. We've reflected twice. That's what we have. And once it was reflected twice, it was also shifted, right? This little starting point on this graph that used to be at 0, 0 is now at 2, -3. So this point has gone 2 units to the right and 3 units down. So I think we have a negative out front. We have the 2 units to the right, which is a +2 minus X. And then we have, shifting it down, -3 at the end. Yeah, I'm going to restart that one because I didn't say that exactly right. Yes, we have this double reflection going on. But when you have that negative sign inside your square root, it's going to also affect your shift. So shifting to the right is usually a -2. Okay, so if we were shifting to the right without that negative sign in there, it would be the square root of X -2. That gets us to the right. However, this negative sign out front means what we really have is minus X -2, right? Because I said it shifted to the right by 2, but this negative sign from the reflection affects those. When you distribute that, what we end up with under the radical is -X +2, and then the negative outside from the other reflection. And then it goes down 3, which is the -3. That's not affected by any of that reflecting, but that inside sign is affected by the negative sign from the reflection, the horizontal reflection, the reflection over the y-axis. So this would be our final answer. Okay, number 29, we have some operations on functions. They gave us 2 functions up here at the top, f of x and g of x, and we're going to do a few things with them. First, we're going to add the 2 together. So if we take f of x plus g of x, we need to have a common denominator to be able to add those 2 together. So we're going to need to multiply in an x squared minus 1 on this first fraction. And we're going to need to multiply in an x on this second fraction so that we end up with 7x squared minus 1 plus 3x all over that new common denominator that we just built. We do want to simplify the top if possible, so let's distribute. And then let's see, I don't know if the numerator is going to factor or not. I don't think so, but let's double check. 7x squared plus 3x minus 7. Can that be factored? We have 7x and x. 7, 7. No, it cannot. I just did a quick check in my head. No. So there is our answer. That is the sum of our 2 functions. Part B, we want to look at the difference of those 2 functions, which is going to be super, super similar because we need that same common denominator. Only difference is we're going to subtract in between instead of add. So we do still want to multiply in the x squared minus 1 on our first fraction and the x on our second fraction. Next step's going to look real similar, except we'll have a minus 3x here. And then if we distribute, again, 7x squared minus 7 minus 3x, that's the only difference between those 2 answers. And there is the difference of our 2 functions. Next up, we want the product of those 2 functions. So we have 7 over x times 3 over x squared minus 1. Not much work to do here when we are taking the product of two fractions. You just multiply across the top, so 7 times 3 is 21, and multiply across the bottom. You can distribute if you want to, but I honestly would just leave it factored. So that's a perfectly good answer. If you distributed on the bottom, you'd have x cubed minus x, also a perfectly good answer. Part D, we want the quotient of our two functions, so f divided by g. Remember, when we divide functions, we multiply by the reciprocal of that second function. And then again, not much to be done here. You just multiply straight across the top and straight across the bottom. And there is our final result. Last question, part E, asks for the domain of that quotient. Okay, when we are using operations on functions, the domain is going to be based on the domain of f and the domain of g. And then if we're talking about the quotient, we also have to make sure that g is not 0 because we are dividing by g. So we get here the domain of f. F was 7 over x. X can't be 0 because we can't have 0 in a denominator. The domain of g, we have to make sure, again, no 0 in the denominator. The denominator of g is x squared minus 1. That means x squared cannot be 1. Take the square root of both sides, we get x cannot be plus or minus 1. So we have to throw x out of our, we have to throw 0 out of our domain. We have to throw positive 1 and negative 1 out of our domain. And then the final thing we need to look at is we have to make sure that the function g is not equal to 0. The only way this function could equal 0 would be if the numerator equaled 0. Since there is not a variable in the numerator, 3 is never equal to 0, so we don't get any more domain restrictions based on that part, the part that g of x cannot be equal to 0. So our final answer for the domain is all reals, except x cannot be -1 or 0 or 1. Here, the directions didn't specify that I had to write it in interval notation, so I just wrote it out in words. Okay, this is our last one, and another problem with our operations on functions. This time we're going to look at composites. So for part A, we need to find f o g, which is the same as f of g of x. Okay, so we're going to use g as our input into the function f. So I like to start off by just replacing the name g of x with the definition for g of x in this problem. G of x is x cubed plus 1, just a substitution. Now we're ready to look at the function f. F is the cube root of x minus 5, but in place of that x, we're going to put our input. So it's going to be the cube root of something minus 5, and our something is whatever we had in parentheses up there. So it's going to be x cubed plus 1. I don't really need those parentheses there, but I just wanted to show you right where I was plugging that in. There's only one little simplification we can do here. X cubed plus 1 minus 5 becomes minus 4. There is the composite f of g of x. And then part B, we're going to flip it around the opposite direction. We're going to find g of f, which this time g is on the outside, f is on the inside. So again, I like to start off by just replacing f of x with the actual function for this problem. So this time f of x is the cube root of x minus 5. Then we're ready to look at g of x. G of x is something cubed plus 1. And what we put in that parentheses is whatever we had in the parentheses in our previous step, the cube root of x minus 5. Here we do get a little simplifying because that radical and that exponent cancel each other out. So we just have x minus 5 plus 1, which leads us to just x minus 4 as our final answer for g of f of x.